and torsional. And we have designed it a couple of shafts based on this. The base such as is equals to 4 divided by pi d naught square 1 minus. So we did it mostly for the circular hollow cross. So where C is a ratio between internal dia divided by the external dia, and for the loading for the bending to MB by 1 minus C. For we have given 16 divided by cube 1 C4 is the kind of things. And for solid shaft, di is equals to 0. That implies C is also 0. That will give you kind of hollow solid cross section. And based on the Mohr circle concept, we have obtained kind of process as 1 to sigma x by 2 x by 2 whole square plus tau square is equals to by 2 whole square plus where sigma x is equal to sigma is kind of tension or comp at different layers in a different manner, and anyway the axial thing is also kind of sigma t. So sigma x is given as such, and here is given by the our corresponding sigma brings to less than tau x less than available, and that's how we have desired. We also seen that ASME gives us bending and torsion, and we have seen that for different KB, MB plus KB, MB square MB given by this T kind of facts that load the table last. Based on the table application, you choose your KB and your things that is in appropriate manner. So once you think, then you go back and the corresponding bending equations, and then you solve for the stresses has to be less than the allowable stresses. Similarly, for the design, especially torsional, we have said that our theta, which is given as L by jg so and theta is the x. Theta critical theta c is taken as 0.25 degrees per is the shaft components. The shaft components are, first one is keys and the second one is couplings. So in today's class, we'll talk about these two, and then we will also see how different keys and couplings are designed, and using the design procedure, we will try to kind of take up a few examples to design the shaft components. So to start with keys, so a key is a machine element or a part used to connect transmission shafts to rotating machine elements like pulley, gears, sprockets, or flywheels. Now, the function, there are two specific functions of keys. They are to transmit torque from shaft to the hub of the mating element, or vice versa. Secondly, to prevent relative rotational motion between the shaft and the hub, at times as well axial motion. Okay, so this axial motion is not taken care if it is for the feathers and splines. Then there are types of keys. So before that, let us have a look at how the key looks like. See, this is the shaft and this is the hub, and these two are joined together with the help of the key that is sitting on it. So if you look from the kind of this side view, then you can see this, the outer one is the hub and the inner one is the shaft, and this key, which is rectangular in nature, will sit in this slot. Okay, so this is the shaft, this is the hub, and you have a keyhole where the key would kind of sit. So the types of keys include first one is saddle keys, and in the other type is the sunk keys, whereas under the sunk keys they are further divided into parallel keys, feather keys, taper keys, and woodruff keys. Now coming to the saddle keys, they look something like this. So the saddle keys is a key which fits in the keyway of the hub only. So if you see, the shaft is circular in nature. When it comes to the keyway, this keyway is cut inside the hub. So as shown in this, and there is no keyway on the shaft. Secondly, there are two types. Firstly, like this, a hollow saddle key, and the second one is, you can see on the bottom side, this is flat, whereas this is curved or hollow in nature. So flat saddle key. And friction is the contributor to transmit the power from shaft to hub or vice versa. and typically used in lightweight application. Coming to the hollow saddle key, it has a concave surface at the bottom of the key that matches with the circular shape of the shaft. Like in this case, this circular shape matches with the circular shape of the shaft. Whereas in the flat key, both the top and bottom of the key are flat and the bottom of the key matches the circular this is the flat surface of the shaft. So in this case, this is the hollow and this is the shaft that is matching. These two surfaces are matching, whereas in this case, you can see this is the flat surface. And this matches with this flat surface of the things. So further, flat saddle key is more resistant to slip as compared to and the cost of the saddle key joint is very low because of the need to machine keyway only on the hub. So that reduces the cost. The second type is Sankeys. So in the Sankeys, that's shown like this. In this case, power is transmitted due to shear resistance of the key, and hence typically applied for heavy duty appliances. Further, the shape of the sunk keys are either square like this, B and H are same, or rectangular. Further, the sunk keys are further classified into parallel or taper based on the tapering in thickness. So in the sunk keys, half the thickness of the keys fit into the keyway on the shaft, and the remaining in the keyway of the hub. So that means machining is required in both the shaft and hub, and hence it is not as economical as saddle keys. Further, tapering is provided for the following reasons. First one is tightness of joint due to the wedge action when hit by the hammer. Secondly, easy removal of the keys. So, and hence, taper on one side of the key is enough. Finally, taper keys are often provided with gib head to facilitate easy removals. For example, this is one such kind of things. You can see that the tapper on the bottom side is not there, whereas on the top side the tapper of 1:100 is provided for this key. Secondly, this is called your gib head, so that this gib head can be gripped for easier removal of this keyway from the key from the keyway. So these are the different types of kind of sunk keys that are available, which comes under the sunk keys. But there are other types such as feather key. Let us see the feather key. So this is a kind of a feather key example. You can see that this key is there on both the hub, as keyway is there on the hub as well as the shaft. This is the keyhole on the shaft, and this is here on the thing, and this is the feather key that is provided on the top. So this will the feather key is kind of things which can give you some relative motion, which generally this hub and shaft will have, can be little bit accommodated. So typically applied in clutches, gear shifting mechanisms, etc. Further, this feather key is also a parallel key that is fixed to the shaft or a hub, so that relative axial movement between them is accommodated. This is clearly this is essentially required because sometimes you cannot have where fixed kind of a keyway. So this, in real applications, you see such kind of the things which requires both axial as well as kind of rotational flexibility. This guy has a axial flexibility, and further the clearance between the key and the keyway allows for sliding motion. So that's how it has axial rigidity. So the next kind of Sankey is a Woodruff key. So if you look through the cross section, you can see the cross section looks rectangular, but it would be something like this, where it is a kind of a semicircular disc with a uniform cross section. So And the keyway which it sits in here is also a semicircular with the same curvature. The recess or the keyway is also semicircular, matching the key shape. So this is typically used in automobiles and machine tools. So one limitation is at this place at this place the net cross section of the shaft or hub decreases, hence stress concentration is observed. So that is the kind of limitations with this kind of Woodruff keys. So these are all kind of different types of keys are there. Now what we'll do is with this different kind of sunk and saddle keys, now we will see the design of the keys. Of a square and flat keys. So the torque MT of the shaft is transmitted to the hub by means of shearing force P or shearing forces P acting on the left and right faces. So these shearing forces are not in the same plane, hence to compensate the angular momentum, a counter shear forces P dash also acts on the system. So in this case, for example, if you look at into it, so if you look into it, because of the torque mt, a kind of shear forces P and P dash starts acting on the left as well as the right surfaces. And to kind of balance this, because they are not acting on the same thing, that will also kind of give you kind of a counter shear forces, which is P dash on the top and bottom surface of the key. So based on this, when you enlarge this thing for the given shear forces, we can see how the failure of the keys would be there. So for that, so if you look into it, because of this two different shear forces, this can break or fracture at intermediate position like this. That is what is shown as the shear failure in this figure. Or because of this interaction happening at the keyway and the key, there can be kind of crushing failure on this contact surface. So that is the second kind of failure that can be observed. So to avoid this, we will see how to design the kind of this keyways to avoid these two failures. The first one is our our force P is given as 2 times mt divided by, because it is mt, I mean P into d by 2 gives you mt, so we have written it in the other way as something like this, because P is acting tangentially to the to the shaft. So, and hence for this shear force, we can derive for this force we can obtain our shear force as kind of P by A, where P is given as 2mt and A is this width is B and this is L. So the cross-section area at which this fracture is sharing is happening is B into L. So I can write it as D times PL is the shear failure. Similarly, for the second one, for the crushing, we can see that sigma C is equals to P divided by this height, we'll take it as half of it, and this length is P by A. Here A is equals to half of it because half is there in the shaft and half the keyway is there in the hub. So the contact coming on both the sides is h by 2. So h by 2 into L. So that implies sigma C is equals to 2mt by d HL by 2. That is equals to 4mt dHL. So this is our crushing failure. So in general, for industrial practice, says B is equals to H is equals to D by 4, and hence for a square, this is the thing, and B is equals to D by 4 and H is equals to D by 6 for the rectangular, and length is typically taken as 1.5 times the D. So this are the typical industrial limits that has been followed to kind of design the or the standards used in the industrial practices. Now we will, since we have seen the design formulas that has to be used, now what we'll do is we will try to do a couple of examples to understand the process of this design. So it is required to design a square key for fixing a gear on a shaft of 25 mm dia. The shaft is transmitting 15 kilowatt power at 720 RPM to the gear. The key is made of steel, which is 50 C4, for which SYT is equals to 460 MPa, and a factor of safety is equals to 3 is used. Now, for this, we need to determine the dimensions of the key and assume SYC is equals to SYT. So for this reason, that means our crushing has same as that of the tensile. So SYC is same as SYT, that is equals to 460 MPa, and sigma C is SYC by factor of safety, which gives us 460 by 3 is 1 Newton per mm square. And our tau allowable is equals to SYS by factor of safety, that is SYT by 2 times factor of safety, that gives us 460 divided by 2 divided by 3, that is 76.67 Newton per mm square. Now the torque transmitted is given as mt with 16 to 10 power 6 with 15 divided by 2 pi. RPM is 720. That gives us 198,943.7 Newton mm. So in our case, assuming an industrial practice, B is equals to H, because it is square, is equals to D by 4. We know that in our case, the diameter is 25 mm. So D is equals to 25 by 4. That gives us 6.25, so approximated to 6 mm. So for this, now we need to have what is the length. So using the shear failure, L is equals to 2 times mt divided by tau allowable times B into D. So 2 into 198, 943.7 divided by 76.67 times B is, let's say, B is 6 mm and D is 25. So that gives us 34.6 mm. Now using crushing failure, so crushing failure says that 4 mt divided by sigma c dh, so 4 198,943.7 divided by 153.3325 into h is equals to 6 mm because it is square. So that also gives us 34.66 mm. So we can say that provide a key with 6 cross 6 cross anything above 34.6 is fine. So we'll go with 36 mm is the thing. So this is how kind of a key has to be, a flat key has to be designed. Okay, so now we have finished with the thing of the flat key. Next we'll go with the different kinds of keys which are like splines. So these splines are keys which are made integral to the shaft or hub, and splines are used when relative axial motion is desired, such as example, we typically find it in our gear shifting mechanism. In automobile gearboxes. So generally, splines are cut on the shaft by milling and on the hub by broaching. So let us look how the splines looks like. You can generally see it in your, let's say you have a bike or something. When you go for next servicing, you can ask this mechanic person to just open the gear and clutch plates. Then in the gearbox, he will show you these kind of things. So these are kind of on the shaft. These are the splines, and this is in the hub, and they are in the matching things. So, and there are different types of kind of splines. So the types of splines are like straight-sided, which is like this, Then there are involutes and serrations, which are like this. So these are straight-sided as I shown you, and you can have an involute shapes or kind of a serrations as shown in this picture. So we will see how the straight-sided splines are designed in this course. So for that, let us look for the torque carrying capacity. The torque carrying capacity of a straight-sided splines is the total torque MT is equals to PM, the pressure, the area, and the radius and the rotation, the radius, where the equivalent radius is calculated as T plus D by 4, and the area, this impinging area on which the pressure PM is acting, can be calculated as D minus T divided by 2 times NL, where capital D is the outer diameter, D is the kind of an inner diameter, and depending upon N is the number of splines that are kind of profiles that you are seeing on the shaft, and L is the length. N is the number of splines and L is the length of the hub, and D is outer dia or major dia, and D is inner dia or minor diameter. So for this, what we'll do is we will try to kind of do a small example to see how we can design a standard spline connection. So for that, let us work on this example. Consider a standard spline connection of 8 cross 52 cross 60 mm for a gear shaft assembly for a gearbox. The splines transmit 20 kilowatt power at 300 RPM. The dimension of the spline are major dia 60 mm, minor dia 52 mm, number of in permissible pressure, normal pressure is 6.5 Newton per mm square, and the coefficient of friction is 0.06. Now we need to calculate length of the hub and force required for shifting the gear. So this, using the splines in the gearbox, we will determine what should be the length of the hub, and also we will calculate the forces that are required in this problem. So for that, what we'll do is first calculate our torque, that is 60 into 10 power 6 into the kilowatt. Here we are doing is 20 kilowatts. So 20 kilowatts divided by 2 pi at an RPM of 300. So it gives at 636,619.7 Newton mm of a torque is there. And then using our equation, which we just presented here, we can calculate the length that is required using the corresponding things by substituting in this one. So length is given as 8m divided by pm n d square minus d square, that is equals to pressure is 6.5, n is 8, d is 60, small d is 52 whole square. That boils down to 109.3 when approximated to 110 mm is the length required. So secondly, now the MT, so due to torque MT, a normal force P acts on the splines, and this P acts on the mean radius of the spline, where the mean radius is given earlier as so our P is equals to MT by RM, because our RM is 60 plus 52 divided by 2 gives mean diameter, and by 4 gives mean radius, that is 28 mm. So 636,619.7 divided by 28 gives us 22736.4 newtons. Since there is a friction between the shaft and the hub, the tangential force that is required, the frictional force, required is mu times P, that is equals to 0.06 into 22736.4, that is equals to 1364.2 newtons. So the force required to shift gear is equals to frictional force, and that is equals to 1364.2 newtons to shift the gear. So this is how you kind of design the keys and splines. And now what we'll do is we'll go to the other part of shaft components, which are couplings. A coupling is a machine part that joins two rotating shafts to each other. So, and they are classified as A, flexible coupling, and B, rigid coupling. In reality, most of the couplings which we see is a flexible coupling, but we will in this course we will try to design the rigid coupling, because that is much easier compared to the flexible coupling. So the advantages are, this rigid coupling is very idealistic in nature, whereas this flexible coupling can accommodate misalignment, both axial and rotational kind of things, and it can absorb sudden loading shocks from sudden loading. So this is kind of advantages of it, whereas the advantage of simple rigid coupling is it is simple in design and inexpensive in cost. So that is kind of thing. For example, we will show you a couple of couplings. So the types of couplings are like a muff coupling, So will look like this. And the second type is a clamp coupling. Case you can see that input and output are kind of coupled using these clamps, and you can see that these kind are bolts. And the next, in generally, these applications you see is in the case of clamp coupling. In the flexible ones, and when it comes to the rigid coupling, these kind of flange couplings. So the rigid flange coupling or something like this. And you can see that in some of the things, you don't have this protection because it is rotating. These kind of bolts can cause can fly off because of dynamic loading or kind of fatigue load. This kind of a flange or outer rim that is there will prevent it from the moving mass. hence this is little protective compared to kind of outer rim. So what we'll do is we will try to see how the design can be done for the both the muff coupling as well as flange coupling. So muff coupling is as follows. So when it comes to muff couplings, so in the muff coupling, it is the simple form, as you have seen. It is inexpensive and easy to design compared to the flange joints or a clamp joints. No projecting parts. Except the key head. Limitation is to disassemble. And requires more length extent in the transverse direction. So the design following design procedure. First, calculate each that is transmit. Its main purpose is to transmit the power. The power gives you, so the power seen is related by this, and the shear stress and the tolerated by this condition. And if you use an inverse formula, you can determine dia. So you give up empty and shear stress tau, you can calculate diameter from this thing. Finally, we have to calculate the diameter of the sleeve. This sleeve. We have a standard, so we'll use calculate dimension of the sleeve. Standard proportion capital diameter of the shaft 10 mm, and the length of the sleeve is given as 3.5 times D. Now for this that we have chosen, check failure case. First one is the torsional in the sleeve using tau is torque into rate by J, where the polar moment of inertia is given as T4 minus T4 divided by 32. The radius can be taken as, for the maximum torsional thing, is on the outer. So we'll take R is equals to T by 2. So, and this tau is less than tau level. Next, this we will determine the standard cross section of Sankey. For that we use equals to capital L by 2, and then check for the shear to coupling, and then we'll break for the day. So let us take down the problem example which we want to solve. Is consider designing a muff coupling which is used to connect two steel shafts transmitting 25 kilowatt of power at 360 RPM. The shaft and key are made of plain carbon steel, which is of 30C8, whose SYT and SYC are considered to be 400 MPa, and the sleeve is made of grey cast iron, which is of Fg200 grade, whose ultimate tensile is equals to 200 Newton per mm square. The factor of safety for the shaft and key is 4 and FOS for sleeve is 6. Then determine the coupling dimensions. So for this, we know that for the shaft and keys, right, is made up of 30C8. So 30C8 has sigma t, that is equals to SYT by factor of safety, that is 400 divided by 4 is 100 Newton per mm square. And the crushing for the keys is SYC divided by factor of safety. We know both are SYT and SYSC same, so this is also 100 Newton per mm square. And the shear stress for the keys can be SYS divided by factor of safety, that is SYT divided by 2 factor of safety, that is equals to 50 Newton per mm square. Now for the sleeve, our shear stress, maximum allowable shear stress, tau is given as SSU by factor of safety because it is cast iron gray. It's SSU, ultimate tensile stress, is 200 and SS the SSU is given as SUT divided by 2 by factor of safety, so that implies it is 200 divided by 2 divided by 6, that gives you 16.67 Newton per mm square. So with this, what we need to do is, this is the given parameters, we have to calculate the torque that is required. So is MT is equals to 16 to 10 power 6. The kilowatts are 25 with an RPM of 360 will give us 663 145.6 Newton per mm, and the shear stress tau is given as 60 mt by pi d cube, gives us tau is 50, 16 into 663.145 divided by pi d cube implies d is equals to 40.73, which we approximated to 45 mm. So with this as the diameter, next is dimension of sleeve. So capital D is equals to 2 times D plus 13, that is given as 2 into 45 plus 13 gives us 103, so approximated to 105 mm. And the length of the sleeve is given as 3.5 times D, so 3.5 times 45 gives us 157.5 160 mm. So similarly, the torsional rigidity J is given as pi d4 minus d4 by 32 is pi into 105 whole square whole 4 by 45 divided by 32 gives us 11530 626.8 mm for, and our outer dia R is equals to T by 2, that is 105 by 2 is 52.5 mm, and the maximum shear stress given on the sleeve is given as MTR divided by J, that is equals to 663,145.6 divided by J is 11530, 626.8 into 52.5 gives us around 3.02 Newton per mm square. So 3.02 is less than 16.67 for sleeve. So it's safe to use this dimensions. Now, similarly, we have to also design for the keys. So for the standard cross-section key design, so let us use a Sankey for D is equals to 45. We can have B cross H using standard proportion as 14 cross 9, and the length of the key in this case L is given as capital L by 2, that is 160 divided by 2, that is equals to 80 mm. And for this key dimension, right, B into H is 14 into this is like the dimension of the key which we assumed. It has to, as we previously solved, it has to resist for the shear stress, which is given as 2mt divided by dBl. So that is equals to 2 into 663, 145.6 divided by 45 into 14 into 80, which is equals to 26.32, and it is less than tau allowable, which is 50 Newton per mm square. Hence it's okay. It is not failing through shear. And the next thing we have to do is for the shear, and next one is the crushing. For the crushing, sigma c is given as 4mt dhl, that is given as 663 145.6 by 45 into h is 9 and length is 80, so this gives out to be 81.87 is less than sigma c, which is 100 Newton per mm square. And this is also okay. So with this, what we are doing is our design for the muff coupling is over. So all the stresses are okay. So this design, this key of this size is fine, and as well as our sleeve of this dimension D and length of is 160 is also good, and the shaft diameter, which is 45, is also kind of fine for the given things. So with this, it completes the muff coupling. In the next time, we will continue with the rigid flange coupling, and then we'll go to the last chapter of doing the springs. So what I would like to ask is, can we take an extra class tomorrow so that we can finish the syllabus?